Assalamualaikum and good day to all panels. In this season, I will share to all of you about my bachelor degree project 2 with the title Muscle and Gripping Analysis of Tenodesis Assistive Device for Tetraplegic Spinal Cord Injury Malaysia people. Before I go through with my presentation, let me introduce myself. My name is Muhammad Afdhal bin Muhammad Zamri and my supervisor is Puan Ruzy Haryati Binti Hambali. In short introduction, tetraplegic is a type of disease that causes paralysis to the patient, where them inability to voluntarily move their upper parts of body. So in this study, I am focusing on the tetraplegic patients suffer injury at level C5 and C6. At this level, the patient unable to grip and grasp an object. There are four main issues for the patient to perform their daily routine according to the current situation because of self-disability, hospital service, patient commitment, and there are few existing assistive devices and difficult to get. The objective of this project, first, to determine issues occur on tetraplegic patient, focusing onto their activity grip and grasp in activity daily life. Second, to develop an automated assistive device that suit to Malaysian people hand sizing according to human factors, engineering, and material selection. Last but not least, to analyze and validate the usability of the assistive device development. For the methodology, the flow chart shows the process required to achieve all the project objectives. Starting from the data collection, design an assistive device and program controller to make automated, and lastly, testing the product. The table shows the relationship between objectives and methodology. In order to achieve objective 1, we need to develop question A and also make a research on the literature review and previous case study. For our second objective, we can achieve by starting collecting interpretive data as a parameter to design in SolidWorks. Followed by second step, design selection and decision making. For mechanical part, show design by using SolidWorks and define the material by using CAS EduPack. To make engineering analysis, it also can analyze FEA by using SolidWorks. For fabrication process, the parts already designed can printing by FDM 3D printer. In order to create automated on the assistive device, the program controller should be used such as Arduino IDE and simulate the circuit by using Proteus software. To achieve objective 3, the assistive device that already fabricated and done integrate with controller should be testing. As input controller, EMG sensor need to be calibrated to get the average output voltage, while mechanical testing towards finger force rate with different angle. Result of questionnaire. For the first question, how far they know about the assistive device? Majority of respondents know about existing of assistive device in the market, and some of them didn't know. For the second question, did they need the assistive device in helping them to perform the activity in daily life? Among the patient votes, agree need the assistive device in helping them to perform routine daily life like a normal people. For the last question, question 3, did they feel the assistive device can help them in performing the activity daily life? For this question, we can identify the importance of assistive device to the patient in order to help them can perform at least simple activity. The compliant finger mechanism allows for some variation in terms of hand size. However, to optimally support the user, the hand module should be tailored exactly to the user hand size and kinematic profile. Therefore, the entire hand module created based on set of key dimension parameters based on result of anthropometric measurement. The parameters after being measured from the user can be fed into the SolidWorks model of the hand module. The figure shows the final design of hand assistive device that is designed in SolidWorks software. The table on the right side is show the bill of material for all components that involved in this design. The functional of each components can clearly seen after we understanding the mechanism of the assistive device. To create linear motion from rotating motor, we implement the conceptual from ball screw mechanism. It clearly shows how the rotating motion can change into linear motion. To pull the nickel strip on the finger in automatic, we need an actuator to do that work. So that's how we try implement the conceptual from ball screw mechanism. To more understanding on the mechanism of this assistive device, on the slide testing assistive device we show how the system works. Figure 1.3 shows the part of fingertip at middle finger. It has a stopper on the upper side. When generating input force, the required force at the fingertip, torque, and nickel strip stiffness in the joint increase with the finger length. Means that by moving the actively nickel strip with an actuator, the relative length of the nickel strip change will result in a bending motion. So the video shows how the finger mechanism works. In this slide show the finite element analysis on index finger that generated by SolidWorks simulation study. On this analysis, we want to analyze stress and displacement for different force applied. In observation, when the force increases, the stress and displacement also increase. We can see the different stress on the red zone between top nickel strip and bottom nickel strip. On top, the stress more on middle fingertip, while at the bottom, stress occur at the front and back fingertip. For displacement, the red zone occur at the front fingertip, which means the higher displacement happen at the point. So this is the circuit diagram that created from Proteus software. On this project, we use Arduino Uno as a microcontroller and input from the push button to generate an output to the motor. To control the high voltage and current load, the relay is used. It is designed to interface with microcontroller. The system works when push button is pushed until 100 milliseconds, so the motor rotates clockwise. While the push button is pushed 2000 milliseconds, the motor will counterclockwise. To stop, push the push button in 2000 milliseconds and the motor will stop automatically. From the circuit diagram, this is a bill of material for electronic component. So we have an EMG sensor, Arduino Uno, relay 2 channel, N20 motor 1000 RPM, diode 1N4007, micro limit switch, and single core wire. This shows how we assemble the assistive device with electronic components in order to make this assistive device automated. The use of power bank as a power supply to the Arduino Uno and relay to channel. It is because the relay needs single supply from power source to power up the relay. For the input, we use push button as a first trial because EMG sensor need to calibrate until we get the constant voltage, so it can substitute the push button as an input controller. The use of micro limit switch on this prototype to stop the motor when the motor moves in clockwise direction means that the micro limit switch in this situation same function like sensor in order to control the movement of motor. In this slide show how we testing of assistive device for the first model and the second model. For the first model show the problem occur at the index finger where the finger started at the early position while others finger move downward when the motor rotate clockwise. It is because of the thread of motor shaft stuck with nut and fork. It also happens when the motor rotates on counterclockwise direction. For the second model, we achieve to move all the fingers smoothly. EMG sensor signal calibration need to get the constant output voltage value that created from it to substitute push button to EMG sensor as input to the microcontroller. The video shows how we testing and monitoring EMG sensor signal voltage on the serial motor in Arduino IDE. The result obtained then transferred to the graph, and from that we can get the average of the output voltage from EMG sensor. The formula above is used to convert analog reading to the output value. This slide explains evaluation on fingertip force testing in different angles. The figure 1.6 shows how we set up the experiment using Mark 10 equipment. On the left side, the graph shows the result of the fingertip force for different angles for each finger. When the angle is increasing, the fingertip force also increasing. This means when the input force supply from the actuator in force range, the fingertip will create bending motion towards the increasing on nickel strips length. In conclusion, the objective 1 achieved by analyzing the data from questionnaire and research from the previous case study in order to understanding issues occur on tetraplegic patient. Second objective achieved by developing a new automated assistive device from combination engineering analysis and program controller. Third objective achieved using technical evaluation and product testing to check the usability and functionality of the automated assistive device. For future recommendation, first, calibration motor management using reed switch or Hall effect. Second, study mechanical systems such as gearing motor. Third, use of material that has mechanical advantage that could replace nickel strips. And last but not least, more surveys on tetraplegic patients due to COVID restriction, less survey and observation that is done.